Swayam Prabha. Digital India. Educated India.
Pressure volume work. So the way it looks like, I have a total reversible work. In that I am subtracting the pressure volume work. That means this entire term is like a non-pressure volume work. What is that non-pressure volume work? It can be anything. It's a mechanical work or electrical work. So for electrochemistry, this non-pressure volume work, we term it as a electrochemical work. Okay. So therefore, the dou G, it depends on the quantity of the material you are burning or quantity of material you are reacting, correct? Suppose I have 1 liter of kerosene and I burn it or combust it, so I get certain amount of delta G. Suppose I have 2 liter of that and burn it, you should get 2 times of this delta G, right? So this delta G reaction and this delta G reaction, they are related by a factor 2, correct? Because it depends on the amount of the material that we are reacting. Therefore, this N depends on how you write the equation. Suppose I write an equation like this, 2H plus 2 electron goes to hydrogen, okay, then N is 2. Suppose I write it like this. So here N is 4. It makes sense because you doubled the quantity of proton here, therefore double the amount of energy will be involved in this process. So how that doubling can be accounted? By using this N, because N here is 2 times of this value. That's how you are accounting, right? So therefore, we know this non-PV work in this case, in our case, is an electrochemical work which can be related by this equation, okay? And in your second year, okay, before doing that, you might have studied about the electrochemical series, correct? Or maybe studying in the second year, electrochemical series, where you will have a zinc 2 plus interface giving a potential of minus 0.76, copper 2 plus giving a potential of plus 0.34, right? Lithium plus giving you a potential of minus 3.05 and so on. So there are many values will be reported in the electrochemical series, and the more negative it is, the element is more electropositive. That means it's a very good reductant. Something is electropositive means what? It is willing to donate the electron. That means it will reduce the opponent. Because it's giving electrons, the opponent will receive and get reduced. So the one which is electropositive is a very good reductant. And in electrochemically, how will you identify such element which will have a very negative electrode potential? What is negative? It's a relative. If I have given you the 2 choice, between those 2 you will be able to find which one is more negative. If I give only 1 choice, it may not be negative enough for a given reaction, that you will not know until unless you perform the reaction, right? So always it's a relative, okay? Negative doesn't mean that you should have a negative sign. 0.4 and 0.3, which is more negative? 0.3 is more negative. Minus 3.5 plus 3.5, which is more negative? Minus 3.5. So it's all relative, okay? So now, suppose I have 2 dissimilar metal, okay, 2 dissimilar metal, say copper and zinc, okay. So, but we know that zinc is more electropositive than copper. What is electropositive means? That material will easily give out the electron, correct? What does it mean? You might have studied in physics something called work function, yes or no? Work function, what is work function? To pull the electron out, right? So work function less means what? Material is more electropositive or less electropositive? More electropositive. So between zinc and copper, which is more electropositive? Zinc. So you bring copper and zinc together. So if you look at the energy level within this material, definitely the Fermi level of zinc will be higher compared to copper. Why? Because work function of zinc is smaller. That means it's more electropositive. That means its energy levels are the maximum level at which you find the electron. In case of molecules, we call it as a HOMO, highest occupied molecular orbital. In case of metals, we call it as a bands. conduction band, valency band, and then there is in between called Fermi level. So the Fermi level of that metal, zinc in this case, will be lying at an energy level higher than the copper. That means it is more closer to the vacuum. So your work function is small. Now if you bring these two together, what will happen? Obviously electron will flow from higher energy to lower energy. So it will go from zinc to copper. Then the zinc at the interface, okay, at the interface, that means within few nanometer, what will happen? The zinc will gain a positive charge. Why? Because it lost its electron. And the copper will gain negative charge because it absorbed that electron. But this way electron cannot keep on moving. Why? Because the positive charge developed at one side will start restraining the electron which is trying to move. So there will be certain amount will be moving. Just like in a chemical reaction, you have something called the chemical equilibrium. What is chemical equilibrium? You mix the reactant, it forms a product. It's keep on forming the product. After some time, it's coming back. After some time, both forward and backward process are equal in magnitude, in rate, right? So at that time, you have a concentration. We call it as a equilibrium concentration. That equilibrium concentration, you wait even for 10 days, 20 days, 1 year, will not change. Why? Does it mean that system is not reacting? It is dynamic. It is converting reactant to product at the same rate, product to reactant. Therefore, as if there is no change with the time is what we observe. Okay. Similarly, when you mix the zinc and copper, when you mix these two, you will see initially electron going. After some time, it will not flow. In other words, the rate of flowing this way and rate of flowing backward both are equal. That means at the interface, we reached a equilibrium. But before reaching equilibrium, some reaction happened. What is the reaction here? Flow of electron is a reaction from one region to another region. So therefore, there will be a net positive charge in one side, net negative charge in the other side, and it is in a space, very confined space, few nanometer. So that space where you have a separation of charge, that space where you have a separation of charge is called a double layer. Why double layer? Because one is positively charged, other one is negatively charged. There are two layers. So it's called double layer. Right now? So in the double layer, what will happen? Because there is a charge separation, you will have a potential developed automatically. Okay? So that's the potential which is reported in the electrochemical series when you dip an electrode in an electrolyte solution. How do you extrapolate this concept to an electrolyte? Same. You take a metal, dip it in an electrolyte solution, maybe the energy level of electrolyte solution may be lower than the Fermi level of the metal. Then what will happen? Electron flow to the solution. Suppose other way, solution energy level is higher than the metal. Electron transfer from the solution to metal. Again, it will not happen indefinitely. There will be an equilibrium. As a result, at the interface of metal and the solution, you will have a double layer generated. That double layer, we now call it as a capacitor. That's a Helmholtz theory, Guy-Chapman theory, all that you will see in your BSc, MSc, right? We will not get into that. So that's how you see electron transfer. Therefore, the energy level in this metal decreases, this metal increases, and they reach an equilibrium. So you have positive charge here, negative charge here. You can see here, all these values are reported here. This is what I mentioned as electrochemical series. How each one of these interfaces gains a particular value by the same concept. If you are taking this material in pure state and standard state, and you would see these values automatically. You may be wondering who calculated this. Was there an electrochemical cell constructed to calculate this? Because all these potential reported against a reference electrode called standard hydrogen electrode. But interesting thing is, this table was not created by electrochemist. It was created by thermochemist without doing electrochemistry. How is it? Correct? That's an example here. This we call it as a Born-Haber cycle. I wanted to go from here to here. That is called standard reduction. If you maintain standard condition of 1 atmosphere, all that. So I want to do this. How I can do that? I can take hydrogen gas. I break the bond in hydrogen gas homolytically. Homolytically means cut exactly in the middle of the bond, giving one electron to one hydrogen, second electron to the other hydrogen in the molecule. Right? Now if you cut that, you will get a hydrogen atom, and then you drop that hydrogen atom in the liquid medium. In our case, in SHE standard hydrogen electrode, what is the liquid medium? It's a 1 normal hydrochloric acid. So you take the 1 normal hydrochloric acid, in that you are going. Then what will happen? All these there is some problem. Okay, let's not put it in the liquid medium first. Let's have it separately. Now we have hydrogen atom. What we are going to do now? We are going to oxidize this hydrogen atom. Okay? So you will get a hydrogen gas, ion gas, hydrogen ion gas. Now imagine now this liquid is interacting with this fellow. Okay? Then what will happen? The hydrogen ion gas will have a ion dipole interaction with water molecules. Why? Because you have chosen 1 normal hydrochloric acid as a medium, a lot of water in there. Then your proton will react with the water that is present in the medium, and you will have something called solvation happening. It's like a bond formation process. Whenever you have bond formation, energy will be liberated. So you can see here, the energy is negative in this process, because from here to here, it's a bond formation. From here to here, bond breaking, so it's positive. From here to here, again it is positive because it's an ionization process. For ionization, you have to spend energy. For breaking bond, you have to spend energy. So thermodynamic convention for spending energy is positive. For gaining energy is negative. So you see, it is negative, these two quantities are positive. So if I want to go from here to from this state to this state, okay, according to Heck's law of heat summation, I can just add these three, which is equivalent to going from here to here. Correct? Yes or no? Because your delta H or delta G is a state property. It doesn't care how I go there. If I know the end, then I know delta G or delta H, right? Here I have not brought into the effects of entropy just to make the calculation simple, because your delta G is a delta H minus T delta S, okay? So now if you can see that, so from hydrogen to H plus ion in water, or if I want to do the reverse, H plus ion in water to hydrogen gas, what I need to do? I add all the three and reverse the sign. Correct? No? That means I am coming from here to here. I add all the three and reverse the sign. That means I am coming from here to here. So that is what I have done here. I have got about minus 429 kilojoule per mole, okay, per mole of proton. Now I know the conversion between the electron volt to joule, so I can use that in place of kilojoule. Then I get minus 4.45 electron volt per H plus particle. Correct? No? It's a purely thermodynamics. There is no electrochemistry here. Right? Now let us do the same exercise for lithium. Lithium, I have lithium metal, I wanted to go here. How will I do that? I just have to atomize lithium, then ionize it. Very simple, right? So take lithium, atomize it, ionize it, add solvent, make aqueous phase. So I want to find out this value. What you do? Add all the three, change the sign. What you get? Minus 1.3 electron volt per Li plus particle. Correct? Any question in that? No question? Now what I am going to do, note down this value, these two value, I am going to put it in a number line. Now this is a number line. For hydrogen it is more negative, for lithium it is here. It makes sense because this is an energy axis. And we know lithium is more electropositive than hydrogen. That means the lithium metal's energy level must be above the hydrogen. It should be close to the Fermi level, close to the vacuum level. Then only it can be a very good reductant, right? Now what I am done, I wanted to make, because like whatever I have done, the Born-Haber cycle, I can do it for any redox couple. I can do it for zinc, I can do it for copper, then I can populate all those values in the number line. I am not doing that here. I have taken only 2 examples. What I am going to do, I wanted to make between these two, one of them as a reference. One of them as reference. Because in your electrochemical series, you might have seen something called reference. What is that? Standard hydrogen electrode. So we always scale the reduction potential of a given element against a reference. How reducing is this element compared to hydrogen? Correct or not? So if you get a value negative to hydrogen value, that means that particular element is good reductant compared to hydrogen. The table only is that. The table tells you how good reductant is this, the element in the series compared to hydrogen. Now I wanted to make the hydrogen as a reference. What I do, this has got minus 4.5. So I simply add plus 4.5. I do the same thing for this guy, same value. So I am now just shifting the energy scale, not doing anything else. The gap between the lithium and hydrogen remains the same. I am only taking up and down the scale. When I do that, this becomes 0, this becomes 3.2 electron volt. Correct? And now we know delta G equal to minus NFE. So if delta G is positive, E will be negative. So I just swap the sign now, because I switched from electron volt to volt. Now you can see hydrogen is 0 volt, where lithium is minus 3.2 volt. Okay, let's go back to the electrochemical series and see. Because I said this is an order of magnitude calculation, I have not considered the entropy changes, so the value should be close but not exact. You can see here lithium minus 3 volt, hydrogen 0 volt, copper 0.34 volt. Am I clear? Any question? See, now there is no electrochemistry, but we are bringing the concepts of electrochemistry through thermochemistry. Okay? Now, what is a reduction? What is oxidation? All those things you know. When you add electron, it is reduction. When you remove electron, it is oxidation. But can you just like that add electron? It's not possible. Further, so many rules are there. You might have studied in the kinetic theory of gases, it's improvisation. What are the things you have studied? Initially, they thought collision of molecules is enough for the reaction to happen. Later, they found it is not enough. Then they said, sufficient kinetic energy is needed to collide. Then also they found it is not sufficient condition. Then they found the orientation also important. What do you mean by orientation? Orientation means, imagine if this is a p orbital, and say if this is another p orbital, in p orbital you have a double dumbbell shape, right? Double dumbbell shape, imagine this is a plus, this is minus. This is plus, this is minus. These are the two molecules which are coming and colliding. Will it react? Will it react? This is plus, this is minus. It won't react. Eh? This will form antibonding. Correct? Now molecule coming like this. Will it react? Chances are there. Why? This is plus, this is plus. So these two wave functions can overlap now. As a result, it may produce a bonding orbital, and hence there is a possibility of PP sigma bond formation. PP sigma bond formation. Imagine this is an s orbital. This is plus. This is also an s orbital. This is a minus. Now these two guys are coming. Will there be a reaction? Whatever the orientation it may be, there won't be any reaction. because the wave function of this is out of phase with this. So whatever may be the orientation, whatever may be the frequency, whatever may be the speed, no reaction. Okay. So who prescribed these rules? All these rules are prescribed by your quantum chemistry. Quantum chemistry says this phase is very important. Okay. So therefore, if it is an s orbital, if this is an x orbital, if both should be either minus or both should be either plus, then when they meet, there can be an overlap, there can be a bond formation, and hence a molecule birth. Otherwise, won't be. Clear, no?
What about hydrogen gas, H2 gas?
H2 gas. Yes, H2 gas comes from H atom.
So S orbital.
S orbital having plus, another H orbital hydrogen having plus, if they interact, it will form H2. Otherwise, it will form H2 in the anti-bonding state, which means no bonding will happen. Right, no? If these two collide, no bonding. If these two collide, there will be a bonding, will produce hydrogen gas. If these two collide, there will be a bonding, will form hydrogen gas. Okay? So you know there are hydrogens, in one case it goes like this, in one case it goes like that. So that decides what is the phase. Okay? So the phase is very important. Then you will have bonding or anti-bonding, whether there is a molecule formation or non-molecule formation. Okay? Now let us extrapolate the concept of putting the metal, joining two metal into the solution. Okay. Now I have a copper metal dipped in the solution. Imagine the copper solution has a LUMO. What is LUMO? Lowest? Yes. And this copper 2 plus is an ion, or it is a molecule, or it's a molecular ion. Ion? Ion is a common answer. Huh? Copper 2 plus is ion. Okay, how many of you saying it's a molecule and also ion? How will I make copper sulfate solution? Take copper sulfate, put it in the water. Correct, no? Eh? Then what will happen to copper sulfate when you put it?
Dissociates into copper ions.
Dissociate into copper ions, into sulfate ions. After that, what happens? How first of all they dissociate? When I add as a salt, it is not dissociating. Only when I add it in water, it dissociates. That means water is doing something, no? So what is it? Solvation, right? Hydration. So it is not copper 2 plus. It's actually copper 2 plus H2O 6 times. Correct, no? So it's an ion, also it's a molecule. Correct? So this particular molecule, it is a copper ion here is in the octahedral crystal field, because there are 6 water molecules are coming in all direction, and there is a splitting in the d orbital of copper, and there is a, as per the safety theory. What happened? Which becomes a ligand? Copper? Copper ion. Ligand is the one which donate electron, right? Yeah. Copper 2 plus is now accepting electron from H2O. So H2O is your ligand. When the ligand combines with your copper 2 plus, it becomes a molecule, but it's an ion. So it's a molecule and ion. Correct? What is the definition of molecule? If you have more than one atom, it is actually a molecule. But it can be ion also. Right? So now if you look at it, copper 2 plus along with the H2O, it forms an entity and it's moving around in the solution, which is what in contact with the copper metal. Am I right? Now what happens? The LUMO, that is the lowest unoccupied molecular orbital of your copper hexa aqueous species, whose energy level depends on the concentration in the solution. Okay? Let me assume I have taken 1 molar copper sulfate solution. So it's not to scale. So its energy level is, say, below the Fermi level of my copper. Then what will happen? The copper metal will pump its electron into the solution. Why? Because there is enough energy level difference. LUMO will accept electron and your Fermi level will donate electron to the solution. So at this interface, you will see there is a reduction going on. That means copper metal that is formed or copper atom that is formed will deposit on this copper metal. Correct? So there is a mass transfer here. What is the mass transfer here? Copper which was in the solution now has been transferred to the electrode surface. And the water which was associated with the copper has been thrown out. Correct? No? Now what happens to the sulfate which came with the copper? It has no pair. So your solution will be rich in sulfate here. Why? Because your copper is lost. And here, since this metal lost electron, this will get rich in positive charge. So in the surface of the metal you have positive charge. Next to the surface of the metal on the solution side, on the solution front, you will have a sulfate ion coolostatically bound with the electron. What is coolostatically bound? Because sulfate ion cannot go any far because the positive charge on the metal is now attracting them. But that's not the only force, because your water is a dielectric medium. That fellow also got a positive negative charge poles. So they also compete with that. Okay, and ion has a finite size. So although I can populate enough positive charge here, it may not be possible to populate the equivalent amount of negative charge here. Why? Because ion has a size. Correct? No? As a result, the ion may not be present only in one layer, it may be in multiple layers. So that region where you have two different charges, and in that region electroneutrality principle is not valid. Correct? No? You take sodium chloride, put it in water, take any tiny volume of sodium chloride water, you will find equal number of sodium and chlorine. Yes or no? Whereas in this case, you take very tiny volume here near the electrode, which is only 1 or 2 molecular thickness. There you will find only negative charge, or you may find only positive charge, or net negative charge or net positive charge. You will not find equal number. Why? Because electron neutrality is not valid there because of this reaction at the interface. You can do the opposite. Suppose I have zinc dipped in zinc sulfate solution. Imagine my zinc sulfate solution is at a higher energy level than zinc. Then what will happen? Now electron has to go from here to here. But zinc is already oxidized. It doesn't want to give electron. Sulfate, where sulfur and oxygen are bonded by a covalent bond. Very difficult to pull the electron from that fellow. Then what can happen now? Whoever weaker will dissociate. Who is weaker now? Zinc. What zinc will do? Zinc will now undergo oxidation, inject its ion zinc 2 plus into solution, and the electron will be deposited to the electrode. That means zinc oxidize, give the electron to the electrode, and it will enter the solution. So since you are adding electron, Fermi level will raise. Right now, Fermi level will raise now. So now you are adding zinc ion here, you are adding positive charge to the solution, so energy level will decrease. So this will raise, this will decrease, then there will be an equilibrium like this. So your zinc metal will become negatively charged, your solution will become positively charged, right? Then what happens? You have an interface like this which is having a potential, okay? Which is having a potential developed automatically. That's the potential we have listed in the electrochemical series, right? Now, in the textbook may not be in your +2, but when you go to higher studies, you will hear something called over potential, application of potential, okay? Application of potential, over potential, okay? So what is it? What do you mean by application of potential? What do you mean by application of potential? Very simple. Let's take the example of hydrogen molecule. Hydrogen molecule. Hydrogen molecule, what happens? You have 2 electrons in the bonding orbital. Now if I add one electron, where it will go? Anti-bonding What is the bond order now? 0.5. That means there is no bond. So then it will become hydride and hydrogen. Hydrogen will have 1 electron, hydride will have 2 electron. How many electron total? 3 electron. So application of potential means adding or removing electron. Adding or removing electron. If I would have removed the electron, that means I remove this fellow. Then what happens? You have only 1 electron now. Again bond order is half. But now how the hydrogen will split? It will split as H plus and H. Why? Total electron available is 1. So H plus has no electron, H has 1 electron, so total is 1. Correct? Now let us do that for a little complicated one, which is oxygen reduction reaction. 1 electron here in the pi, second electron in the pi, 2 more electron to this sigma. This is a molecular orbital diagram of an oxygen molecule. So in your plus 2 you might have studied the sigma 1s, sigma star 1s, 2s, star 2s, 2p. Then after nitrogen you see some change in the order, all that, right? So now if you see in that order, if you put it, that is called molecular orbital diagram. Now you can see why oxygen molecule takes 4 electron, because oxygen molecule has got a double bond. Add the first electron, bond order will be how much? How much? First electron when you add, how much is the bond order? When you add second electron, 1. When you add third electron, fourth electron, it is 0. There is no bond. Correct? So by doing this way, I am able to break the bond one by one in case of oxygen. And as a result, at the end, I get 2 oxide ions, O2 minus, 2 oxide ions. Because each oxygen carries 2 negative charge, there are 2 oxygen, you will get 2 O2 minus. Clear? So this is called application of potential. You should not be confused what is application of potential. It is either adding electron or removing electron. Okay. Now we will come to the solid state chemistry, because in the next 1 hour or so we will do some electrochemistry with the solid state chemistry in the context of lithium ion battery. Okay. Now some of you might have to study, not all of you, about the close packing. Okay. So I have taken the example of cubic close packing. What is cubic close packing? I take a 2D layer of atoms arranged this way. Look at this 2D layer. Connect any 3 atoms nearby. What is the shape you get? I have cold. I can't hear you. You have to be a bit loud. Triangle. You take these 3 atoms, triangle. So first layer is red layer, triangle layer. So it's called triangular lattice. Second layer is again a triangular lattice. But in 2D they are same. But in the 3D I have put it in a different coordinate. They are not overlapping one over the other. That's an upset. Now third layer, I can put it right here or right here. If I put it here, third layer is distinct from the other 2 layers. Right? Then we call it as A, B, C type of packing. Why? Why A, B, C? It just tells these 3 layers are distinct in their coordinates. So A, B, C. Again after that again A, B, C. It repeats. So if you put the orange one, which is the third layer, and then if you connect the atoms the way I connected, what you get is a face-centered cubic lattice. What is face-centered cubic lattice? If you take a cube, let us put atoms in the corner. Also in the face center. Okay, then it is called a face centered cubic lattice. How many faces are there? 6. So this atom is at the center, and this I am going to call it as a unit cell. That means the unit cell will repeat in the space. It will continuously go on like that. Okay. So if that is the case, this particular atom is at the interface of 2 unit cells. Correct or not? So that means the 6 face centered atoms contribute all together for a given unit cell. What is the contribution? What's the contribution? There are 6 face centered atoms, and each of those atoms has interface of 2 unit cell. Then for the given unit cell, how much face centered atoms are available? Question, repeat. See, that atom is at the interface of 2 unit cell. So what is the contribution of that atom for 1 unit cell? Now 6 such atoms are there. What is the total contribution of the 6 atoms for 1 unit cell? That's what I am asking. Okay, so you have 3. Similarly, what about the atoms in the corner? What is unit cell? Unit cell is a smallest volume which repeat itself to make a lattice, which repeat itself in space without leaving any void. Okay, like if you have a cube that you might have played the Rubik's cube, right? So you take those cubes and you assemble. So you will not see any gap between the cubes. You keep on assembling, right? So that smallest volume which you need to build the largest structure without leaving any void, it's called unit cell. So now what about the atoms in the corners? How many corner atoms are there? What is their contribution, all the 8 together for 1 unit cell? 1/8. Why? Because the corner is a common point for, in 2D you see the corner is a common point for 4 unit cell, right? Correct, no? If you take this point, corner, 1, 2, 3, 4. But lattice grows also in the z direction. So that means this point will be a junction of 8 unit cell. Correct? That means each atom will give only 1/8 to the given unit cell. So altogether 1. So we have 3 coming from the face center, only 1 coming from the corners, totally 4. Right? Totally 4 atoms contributing to the unit cell. Now that's what I have done here. You can see I have reduced the size of the corner atoms, kept the size of the face center atoms as such, so that now you can connect these 4 atoms. What is the shape you get? Square. And then connect them to these apex atoms. What do you get? You get a square base with a pyramid, both above and below. So if you have a double pyramid with a square base, we call it as a octahedra. Octahedra. Square base, not triangular base. Okay? When you get triangular base, when you have a 2 tetrahedra attached, you get triangular base. Okay? So now you can see in this case, the void here, the void means there is nobody here, that's why I call void, or interstitial positions. This void here is empty space, and if I connect all the atoms here, then you will get a shape called octahedra, but that shape can be built without even these atoms having 2D shapes. What is the 2D shape you will use to build this octahedra? Very good. The 2D shape you will use to build that is the square comes because of triangle. We don't need square. Okay, 8 triangles you need if you want to build one octahedra. That is why it's called octahedra. Octa means 8. Okay, so it's octahedra because 8 triangles you use to build this a closed shape, and inside that shape there is a void, and that void is octahedral void. Okay, and now you see where else this octahedral void is present. I can go to the edge center. This is edge center, and borrow 2 atoms from the nearby unit cell, and you can visualize an octahedra here. Correct or not? So you have octahedra here in FCC lattice, in the body center and in the edge center. Now tell me, how many edge centers are available with one cube? 8. 12. Tell me, what is the contribution of each edge center to the unit cell? 1 by 4. So that means how many total? 3. There is 1 in the middle, 4. So there are 4 octahedral voids belong to one unit cell. How many atoms we calculated earlier for one unit cell? 4 atoms. If you have 4 atoms, 4 octahedral voids. N atoms, N octahedral voids. Okay? We generalize. N atoms, N octahedral voids. Now let's look at another one. We have voids here also, here also, here also, here also. How will you construct that void? Take one corner atom, the 3 nearby face atoms, face centered atoms. You connect that, it becomes triangle. Each of those atoms you connect to this apex atom. What is the shape you get? Tetrahedra. Tetra means 4. That means it has a 4 triangular face forming that. Clear? 4 triangular face forming a closed object called tetrahedra, which includes tetrahedral void. Tell me how many tetrahedral void belong to one unit cell. Quick, did I hear wrongly? Someone said 8, right? Who said it? Huh? Raise your hand. Very good. So, good. So there are 8 tetrahedral voids. Correct, no? Then we had 4 atoms, 8 tetrahedral voids. So I generalize. If I have n atom, I will have 2n tetrahedral voids and n octahedral voids. Clear? So if you have a lattice wherein the unit cell delivers you with n atoms, n octahedral void, 2n tetrahedral void, that has to be face center cubic lattice. Okay? Now look at this animation. In space, we have an octahedra and we will have attaching the tetrahedra on that. Okay? How do we understand that? Go back. These 3 atoms which forms one of the face of a octahedra is the same 3 atom which is here. Yes or no? Therefore, I will say the octahedra and tetrahedra are sharing a common face. In other words, we have a face shared tetrahedra and octahedra. Since we have an octahedra with 8 face, there will be 8 such sharing. So there are 8 tetrahedra decorating around octahedra. And now you visualize this again, you will get it. Okay. What time we have to stop, ma'am? Huh? 2:55. Huh? Now let us do it a little differently. because all of you might learn sodium chloride structure, which is a rock salt, right? So this is a cube. We have atoms in the corner and the face center. That's an FCC lattice. And what I am going to do now, I am going to put some atoms in the voids also. Which voids I will put? For now, I am going to add atoms only in the octahedral voids. Okay? Where are the octahedral voids? Where are the octahedral voids? In the edge center and right? So you have atoms in the body center, edge center, and this structure is called sodium chloride rock salt structure. Okay? It's very simple to draw this structure if you do it step by step instead of memorizing it. What is the step by step? Draw a cube, put atoms in the corners and the face center, take another pen, different color, put atoms in the edge center and body center. Then you will get sodium chloride structure. Right now?
Sir, is there a void in the center of the cube also?
Yeah. We have seen that, right? And what we are going to do today, derive some structure which is useful for battery from this lithium ion battery. So what we are going to do, take sodium chloride, 2 units of that, make it Na2Cl2. So it is not a molecule. Na2Cl2 is not a molecule. Why? Because what's the difference between the molecule and this salt? They are very different. This extended material like sodium chloride are very different from these compound. Why? Then?
Molecules have weak forces of aggregation, but salts have strong ionic bonds connected.
Any other way?
So NaCl is considered as a formula unit, whereas this.
Why they are considering as formula unit? Because it is not a molecule. Correct, no? If you see in methane, these all 4 bonds are covalent. Now go to another methane. These all 4 is covalent. So what is there between them? Van der Waals. So you can isolate one CH4 any time. So it's a molecule. Now let us take sodium chloride. In all directions bonding is same. Then how will you isolate one sodium chloride? Not possible. Any direction you look at it, it looks same. How far you go, it looks the same. So therefore, it is not a molecular material. It's an extended solid. So for extended solid, smallest unit we call it as a formula unit, which is NaCl in this case. So therefore, I have a freedom to write it as Na2Cl2, NaNClN, NaMClM. Is my wish. Now what I am going to do, this chloride, I am going to substitute with oxide. Chloride with oxide. How many chloride is there? One of the sodium I substitute with lithium. Another sodium I substitute with cobalt. Then this fellow must have the same structure or framework, same framework like sodium chloride. Only thing here is who is making framework. Anion generally makes a framework because it's a bigger. So chloride was making framework for sodium chloride. Here oxide makes framework. So framework is same in both. Only the cation is changing. So therefore LiCO2 must be having the same kind of a lattice like sodium chloride. But we don't call it as a rock salt structure, but as same framework as NaCl. That means lithium is also in the octahedral voids, cobalt is also in the octahedral voids. There are 2 oxygen. If you have N oxygen, how many octahedral void? N octahedral void. I have 2 oxygen, how many octahedral void? 2 octahedral void. One given to lithium, another one given to cobalt. That means 50% of your octahedral voids are occupied by lithium ion, remaining 50% are occupied by cobalt ion. What is the oxidation state? Formal oxidation state of these 2 ions? Li, cobalt, 3 plus, Li plus, cobalt 3 plus. Okay, this is the formal oxidation states of these two ions. Now with this we will stop first session. You can see I have redrawn that sodium chloride structure. I have redrawn. All the red atoms are your oxides. All the red atoms are your oxides. Where are they? Corner and face center. All the green atoms are your lithium. Where are they? Edge center. All the blue atoms are your cobalt. Where are they? Edge center and body center. Green again, edge. So number of atoms here are not same. One extra in cobalt. Alright? One extra in cobalt. Therefore, this is not a unit cell. Unit cell is the smallest volume which repeats itself. So this cannot be. Why? Because this does not obey the formula unit LiCOO2. It gives you Li 1.5, CO 2.5, oxygen 4. But it is correct. How it is correct? All you need to think is little different. Anion framework is still the same, but unit cell shape is different. You can draw a rhombus unit cell now, such that you get that formula LiCOO2 out of this lattice. Okay? So if you do that, then you will know now it's the same rock salt lattice, but unit cell shape is different. Why? Because it also has to satisfy this rule. The formula unit, it should come out of that LiCOO2, but it's not coming out as we have drawn. Therefore, we have to reconnect such that that formula unit comes out of this. Understand? And you will also study in physics probably Miller indices. What is Miller indices? Miller indices is a way to represent a particular plane in crystallography. Okay, in crystallography, a particular plane. How do you know at what height you are flying in the flight? Because you will use mean sea level as a reference to find how high you are from the ground. Correct? No? Like that, we can say that air traffic control might say that, okay, you are a domestic flight, you fly in this plane. You are international flight, you fly in this plane. You are an ATR flight, you fly it in this altitude. Correct? Because there's a different plane. So how do they name the plane? They name the planes using the altitude. Similarly, crystallographer name the plane in a crazy way. That's what we are going to see now. Suppose if this is a unit cell, I wanted to go, and this is my origin, I can choose any one corner as my origin. From here you travel 1 unit along the x-axis, 1 unit along the y-axis, 1 unit along the z-axis, 1 unit. Then you connect all the 3 points and you will draw a plane. And that plane is called 111 plane. 1 unit along the x, 1 unit along y, 1 unit along z. Take the inverse of that. That is 111. That is called 111 plane. Suppose I have something like this. What is this plane? This is my origin now. Okay. I travel 1 unit along here. I travel 1 unit along here. I am making my plane parallel to the z-axis. That means it's not cutting. So I have 1 unit along x, 1 unit along y, and never cuts. Okay, parallel. Take the inverse. So 1, 1, 0. Okay. This plane is called 1, 1, 1, 0. That means it just goes through the face diagonal. It goes through what? The face diagonal of your cube. Face diagonal of your cube. That is 1, 1, 0 plane. Okay. Similarly, if I go only half a unit here, half a unit here, half a unit here, that is 2, 2, 2. Why? Take the inverse of that. 2, 2, 2 plane. So if I have a plane here which is parallel to this plane, which will be called as a 2, 2, 2 plane.
Why did he take the inverse? Why couldn't
It's
he
only
have just-
notation. Okay? Because we don't want this infinity there. Okay?
டெக்னிக்கலா பார்த்தா எல்லாத்துலயும் 0 0 மூவ் பண்ணா இன்ஃபினிட்டி 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 வரும்.
Elachi?
எல்லாத்துலயும் 0 0 மட்டும் மூவ் பண்ணோம்னா இன்ஃபினிட்டி 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 வரும்.
Yeah. 0, 0, 0 means you are not making a lattice, you are right at the point. Correct? You have to travel if you want to make a lattice. You don't want to go anywhere. There is no concept of plane. It is 0 means it is a point. Right? Clear? So we will have here 2, 2, 2 planes. Suppose 1/3 only if I am going. 1/3, 1/3, 1/3. Then it's a 3, 3, 3 plane. Okay? So you have a 1, 1, 1 plane. You have seen halfway 2, 2, 2 plane. 1/3 of the way 3, 3, 3 plane. But if you are going through face diagonal 1 unit in x and y, then it is a 1, 1, 0 plane. Correct? So like that, there are ways to denote this plane, which is called Miller indices. We don't need, I just gave you because we may use it in the coming lecture. Okay, we'll stop here. We'll discuss. Yeah.